Today we're going to talk about anti-aliasing, and not the kind you know from video games, but anti-aliasing in 3D printing. This is a new method of non-planar printing that can be activated by a simple checkbox in a special version of Bamboo Studio, and that tremendously reduces the stair-stepping effect on FDM 3D prints. With just a bit of slicer trickery, you get sub-layer accuracy, especially on shallow sloped surfaces. And this method doesn't require any special hardware, is more or less universally usable, and with just a bit more work could make 3D prints smoother and more accurate. So let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. This video is sponsored by Mitutoyo and their new Surface Test SJ220 portable surface roughness tester. This amazing piece of measurement equipment helped me to put numbers to something I was previously only able to subjectively grasp by feeling and scratching the samples. But more on that later. Almost every 3D print that is made these days is in reality more a 2.5D print. What I mean by this is that even though the process itself produces a three-dimensional object, the way parts are typically printed is by stacking two-dimensional layers on top of each other. Most of the time, the print head only moves in a flat plane when laying down material, and only after one of these layers is finished does the nozzle move up by one layer height and continue printing the next one, creating the typical stair-stepping effect we see on additive parts. And this is still how most thermoplastic, resin and even metal 3D prints are produced today. The reason for this approach is pretty simple. 3D printing preparation software is called a slicer because it cuts the three-dimensional models into thin slices and then processes these slices and fills them up with print moves. This isn't just mathematically simple and robust, it also avoids collision with other parts of the print because the print head always moves above the highest point of the model. So in order to get away from stair steps, we've seen several different approaches to non-planar printing over the last few years. Non-planar means that the layers are no longer a flat plane, but instead curve to better follow the geometry. Sometimes this approach is only used on the top layer, but in other cases every layer is printed in a real three-dimensional fashion. So you might ask yourself why non-planar printing is not a feature in any major slicer today. In my opinion, there are two major reasons for this. The first one is that non-planar printing is simply complex. There are so many edge cases where it just doesn't work. So there's currently no general non-planar algorithm, and most examples focus on relatively simple geometry. The second reason is hardware. If you want to print non-planar, the print head is constantly moving up and down. And since the cooling shroud of a printer is typically very close to a nozzle, the slicing algorithm has to ensure that no part collides with the already printed sections. This has led in the past to some very interesting hot end and cooling shroud designs. So general non-planar slicing in this sense is simply not easy, and that's why we don't have it yet. But this is exactly where Z Anti-Aliasing, or ZAA for short, comes in. If you've ever played a video game or worked with computer graphics, you know that anti-aliasing is used to reduce the visible stair-stepping you get when diagonals or curved edges are approximated by square pixels. Without anti-aliasing, an angled line on a screen can only jump from one pixel to the next, creating that jagged, blocky look. Anti-aliasing works by slightly adjusting or blending those pixels so you get the edge that follows the intended shape more closely, even though the underlying grid is still there. Z Anti-Aliasing applies the same idea to 3D printing. Instead of square pixels, you're dealing with flat layers stacked on top of each other. And instead of smoothing things in X and Y, ZAA smooths the surface in the Z direction by making tiny controlled height adjustments within a layer. The part is still sliced into layers, but the top surface is no longer forced to be perfectly flat at each step. It can gently follow the actual geometry of the model. The initial idea for this appeared in a 2017 paper by French researchers. Tianinova, without even knowing of the paper's existence, implemented a similar idea 2 years ago as a post-processing script for Orca Slicer, which Alexander Dobkin then used as a basis for creating a version of Bamboo Studio that I've been using for this video. You simply download it and get a new option under the Quality tab in ZAA Bamboo Studio. When you turn it on and slice a part, you can already see that layers on sloped surfaces that used to be completely flat are now slightly contoured, following the shape of the part much more closely. When you print a part, it doesn't look dramatically different at first glance compared to one without CAA. But when you touch or scratch it, you immediately notice that the discrete steps on the top surfaces are almost gone, and the print feels noticeably smoother. You can still feel that the surface has a roughness similar to that of any other top surface of a print, but the steps are almost gone. The way Z Anti-Aliasing works is both simple and very clever. First of all, it only affects top surfaces of a part, so most areas of a print aren't touched at all. To illustrate this method, let's look at the side of a simplified part. The dashed line represents the edge of our geometry. In conventional slicing, the part is cut in the middle of a layer and the nozzle moves on a plane while extruding plastic. Then the nozzle moves up by one layer and does the same thing again, creating the typical FDM stair steps. Z Anti-Aliasing is smarter than that. The algorithm projects the toolpath of up-facing outer surfaces onto the actual geometry and therefore follows the shape of a part by dynamically varying the layer height in a small margin. This way you avoid most of the major collision problems associated with other non-planar approaches while still following the slope of a part almost perfectly. And this doesn't just get rid of stair-stepping. Dimensional accuracy also improves because you get rid of the over-extrusions in some areas and fill voids in others. And you can't just feel that effect, you can even measure it. This is where today's video sponsor Mitutoyo comes in, and I'm seriously honored to have them support the channel and projects like this. For more than 90 years, Mitutoyo has been building precision measurement equipment in Japan, not just for industry, but also for serious makers. I'm sure many of you have one of their calipers on your desk or in a drawer somewhere. For this video, they provided their new Self-Test SJ220 portable surface roughness tester. It uses a tiny diamond with a stylus tip radius of only 2 micrometers that carefully drags across the surface of your part and measures even the smallest deviations. Thanks to its compact size, it's portable and can be used almost anywhere. The intuitive touchscreen lets you quickly adjust settings or analyze your measurements. And not only is the built-in battery charged by USB-C, it also offers a wide range of communication options. Check it out using the link below and see it in use right now. Let's start by measuring the effect of Z Anti-Aliasing on these simple samples with surface angles of 5, 10, 15 and 20 degrees. Both sets were printed at 0.2mm layer height in PLA, with the only difference being that ZAA was enabled on one and disabled for the other. Even though you can't easily see the difference from above, a closer inspection reveals visible stair-stepping on the conventional part, while it's almost gone on the ZAA sample. I measured each slope twice by gently placing the measuring tip of Mitutoyo's surface tester onto the part. Within a few seconds, the tester drags the tip over the surface, measuring the surface profile, and then processes it to give me the roughness values. I focused on RA, which is the arithmetical mean roughness. In simple terms, it's the average height deviation of the surface from a perfectly smooth reference line. If you imagine dragging your finger across the surface, RA is a good indicator of how soft it feels overall. Lower RA means a smoother surface. The biggest improvement is visible on shallow slopes, where stair-stepping is normally most pronounced. Here, the conventional RA roughness is around 80 micrometers, compared to just 25 micrometers with Z Anti-Aliasing turned on. That's more than a threefold improvement. As the slope angle increases, the conventional roughness gradually decreases, but the ZAA parts are always smoother and, interestingly, at a very consistent level. At some point, here at 25 degrees, the curves converge. At this point, the step length is smaller than the extrusion width, so the path can't be moved anymore in the Z direction. At even steeper angles than this, ZAA simply doesn't have an effect anymore, and you're left with the roughness inherent to the technology. All of these numbers show that Z contouring clearly works. Visually, it may not look as dramatic as some other non-planar approaches we've seen in the past, because the top surface is still divided into individual layers and you can see the boundaries. But there are still some very significant advantages. One of them is post-processing. When sanding and filling parts in the past, especially on very shallow slopes, you often had to fill deep voids and sand down excess material over and over. To illustrate this, I printed the top halves of a sphere. This could be something like the top of a helmet, one with ZAA and one without. I measured surface roughnesses in 3 directions. The conventional part started with an RA of 50 micrometers, while the ZAA part was already down to 21 micrometers. I then applied spray filler, which really highlighted the stair pattern. After letting it dry overnight, I lightly sanded both parts and measured them again. This first post-processing step roughly halved the roughness of both samples, but neither was perfect yet. After a second round of filler and sanding, the ZAA part again nearly halved its roughness and already felt extremely smooth, while the conventional part only showed a small improvement. In the end, the conventionally printed part only reached the same roughness level as the ZAA part had straight off the printer. And I think that clearly shows how powerful this technique can be, especially for anyone who post-processes their parts or needs smooth sliding surfaces in mechanical applications. The other big point is print time. I've printed several test parts at different layer heights because with conventional slicing, the thicker the layer becomes, the rougher they are, simply because the steps between the layers become steeper. But with Z Anti-Aliasing, we can smooth that out. When we add the ZAA results to the plot, something interesting shows. A part printed at 0.2mm layer height with ZAA is just as smooth as one printed conventionally at 0.1mm. And it gets even crazier. If we increase the layer height to 0.3mm and keep ZAA enabled, the surface roughness stays almost exactly the same. This means we can theoretically print at 3 times the layer height while keeping top surface roughness nearly constant. A few years ago, when printers were primarily speed limited by their movement speed, this meant massive print time savings. Today, with fast machines that are often melt rate limited, the benefit is smaller, but a print time reduction of around 50% is still very realistic for some parts because Z Anti-Aliasing shouldn't add a significant amount of print time due to only very small additional print movements in the Z-axis. You might ask yourself whether variable layer height, a slicer feature we already had for years, could also be a good solution for smoother top surfaces, and in a way it does, but it has 2 downsides. First, it adds more layers, which increases print time. Second, while it works well for simple parts, complex geometries almost always have at least one shallow section at every layer, which forces in the end almost the entire part to be printed at a lower layer height. Z Anti-Aliasing, on the other hand, lets you print the whole part with thicker layers and only modifies the tool paths exactly where it's necessary. Up to this point, this all sounds pretty amazing. So you might be wondering why this isn't already part of mainline Bamboo Studio or Orca Slicer. As always, there are some challenges, but in my opinion, they are way smaller than with other non-planar approaches. My initial explanation has been a bit simplified, and in reality it's a bit more complex. You might have already noticed on some of the parts that surface quality with ZAA parts can vary on a print. Earlier I said that ZAA avoids the collision problem of other non-planar approaches. And while that's mostly true, it's not entirely. Even though the cooling shout isn't an issue anymore, the nozzle itself can still collide with already printed material because the lower part of a nozzle is typically wider than the extrusion. The current ZAA implementation takes planar tool paths and adjusts only the Z component to better follow the geometry. This can lead to problems depending on the order in which the lines are printed. If a surface is filled from low to high, everything works fine. But if it is filled from high to low, the side of the nozzle can collide with the previously printed line, leading to rougher surfaces. On complex prints, this is almost unavoidable and shows on parts right now. Solving this properly will likely be the biggest task before a ZAA becomes a fully finished feature. We should already be able to get better results if we used a pointy nozzle, where the lower part doesn't have that big flat section anymore, but this would kind of defeat the no hardware modification necessary premise. There is also another solution. The original 2017 paper splits extrusion paths by height and prints them from the lowest to the highest, avoiding interference entirely. But since this creates a large number of individual paths, the authors also propose an optimization algorithm to reduce travel moves and also place the remaining seams in less visible areas. Going into more details would be too much for this video, so if you're interested, I've linked the paper below. There are also still some minor bugs and edge cases in the current implementation. Sometimes I had gaps between the layers because the Z height wasn't somehow reset. I also noticed gaps in my top layers. Upon further inspection, I saw that on flat sloped surfaces, the extrusion transitioned from low to high or high to low, but it jumped depending on the direction. You see, our 3D printer G-code doesn't have a command to move from point A to point B and transition from a low to a high material flow, for example, as it would be necessary for our variable layer height. So we typically divide paths and vary flow in steps. Sometimes the current implementation does that, like on the sphere, but it doesn't do that on my wedges. But this, in my opinion, can all be polished, and overall I think this is a technique that could realistically be integrated into mainstream slicers, unlike many other non-planar approaches that are more complex and are clearly limited by hardware constraints. In my opinion, Z Anti-Aliasing is a very exciting technique that again shows how much potential still lies in clever slicing algorithms. The current Bamboo Studio implementation is already a great proof of concept, and with a bit more development, this could become an amazing option for smoother and faster prints, without all the complexity of full non-planar printing. A big shout out goes to Thea and Alexander for the massive amount of work they put into making this already usable today. But what do you think about Z Anti-Aliasing? Would you like to see this as a standard slicer feature, or would you rather have true non-planar printing instead? Let me know in the comments. Thanks for watching, everyone. I hope you found this video interesting. If you want to support my work, head over to Patreon or become a YouTube member. Also check out the other videos in my library. I hope to see you in the next one. Auf Wiedersehen and goodbye!